Hi, I'm Jade. So a while ago, I gave this talk at my university, which is Staffordshire University. I also did this talk internally at the company I work at, but that's not the point. Quite a few people missed this talk just because like timing, and so I kind of said I'd re-record it for them. But also, I guess there's going to be people outside of that want to see this. So yeah, here we go. I guess so. Yeah, as you can kind of tell from the title, it's kind of on how graphics worked on fifth gen consoles. Now there's quite a few consoles that are considered like fifth gen. For this talk, I kind of just grabbed the images of the ones that Wikipedia lists. But I personally, I only really care about like these three, right? I mean, I'm not against talking about the other two there, but they're just, yeah, outside of the scope of this talk. So these are the main things I'm going to be talking about. And we're kind of just going to jump straight into talking about them. So the Sega Saturn, to actually like get how it works, we kind of need a bit of context and history to kind of understand the underlying principles that it's kind of based off of. So first, you kind of got to understand how a lot of 2D consoles worked. And now this does seem unintuitive, right? I mean, these are all 3D consoles. I mean, all of these three here, they're all 3D. This is like the 3D generation. But just stick with me here. So the way that 2D consoles worked was based on tiles and tile sets. And the details of this vary slightly from console to console. But a tile is always a square. It's typically 8x8 pixels, but again, it varies. But it's just a square of pixels, right? And your tile set is just like a big 2D grid of tiles. And so you've got your sprites and your background layers. Sprites are just parts that can move independent of the background, right? They can all move at their own separate pace. Now I've kind of taken an example from the Game Boy here, but there's a lot of details here that aren't particularly relevant. All we really care about is just these numbers, right? But so you can see if you look in the tiles, right? The first space is blank, and then after that it's kind of one like the tile 1 and tile 2, right? Because it's zero indexed, because that's how computers typically are. And if you look up at the sprites, you can see that the one that looks like it's using that first tile is 1. The one that looks like it's using the second one is 2. And the next two are using the same tiles, but they're flipped. And if I actually go back here, the lowermost byte, the reason it's 2-0 is because it's saying that it's flipped. Now, the important thing to take away from this is that when a sprite uses a tile, the entire tile is drawn. Right? If I go back to this, none of the bytes there specify how much of a tile to use. The only thing that's kind of specified is just use this tile, and that's it. And yeah, that's kind of one of the important takeaways with this. So now we can have to get into the history part. Originally, the Saturn, it was supposed to be like a 2D powerhouse, right? And then I see the PS1 here. It wasn't just the PS1. Sega kind of saw all the competition. They saw the fact that this was a generation that was made for 3D, and they decided like, oh, we need to make this 3D now. They'd already done quite a lot of work with the Saturn at this point, so they decided to instead retrofit it so that it works with 3D. Now, the kind of result of this is that the architecture of the Saturn is very confusing. There's 8 different processors, 2 of which are the main CPUs, which it has 2 CPUs in a master servant setup. So it's a whole thing. But yeah, so we're just going to talk about the architecture now. I'm not going to go too in depth to the architecture. I'm only really focusing on the graphics stuff here. But yeah, so the first chip that we're going to talk about is the DSP. Now the DSP is used for speeding up vector matrix maths, right? And one of the ways it's able to do this is it's able to execute 6 instructions in parallel. And so what this means is that each of the six different parts of this chip, so the part that loads stuff, the part that adds, the part that multiplies, they can all be working in parallel. But this kind of means that you have to be writing out code that has 6 instructions in one line. That's not really the kind of thing you can really do in a higher level language. So you got to write an assembly, and then you can see how the complexity is already starting to build up quite a lot. So the next chip is the VDP1. The VDP1, it's pretty simple. It kind of is predominantly used for drawing sprites. And the second last chip is the VDP2. This one just is used to draw backgrounds, right? Now, I do want to elaborate a little bit on the sprite stuff here. Now, the VDP1, it draws a different type of sprites, like from the ones that we saw earlier, but fundamentally it's only ever drawing sprites, right? And so this kind of means that because like what we were drawing earlier was always a square, or in this case it'd be a rectangle, our lowest primitive is actually a quad, not a triangle. And this is kind of very different from all the other consoles of this era. To my knowledge, everything else is using a triangle, and the reason for this is because you can put two triangles together to make a quad. So using quad specifically as your primitive or lowest primitive is kind of it's very unique. Now, kind of as I said earlier, the VW1 sprites, they're not exactly the same as the ones we saw before. So the ones we saw before, you could specify what tile they were using, what position they had, if they were flipped. It's not very much there to specify. The sprites in the Saturn, they can be distorted, so you can just specify an arbitrary position for each vertex, and it's able to kind of just figure out how to draw it. Like before, they can also be textured, but this time they can also have like either be a solid color, or they can be like a mix of a texture and a color. Now to kind of show this, I've just taken a video from a Game Hut video. I've taken a clip from a Game Hut video, just kind of showing how it distorts. And the main thing to take away from this is that, as you can see, it's always a quad, no matter what you do. That's kind of it's important to kind of keep that in mind. Okay, so how do I actually draw sprites with the Saturn? That's the question then. So it's pretty straightforward. You build up a table of commands in memory. You then send that table over to VRAM, and that's it. It's actually pretty straightforward to actually draw sprites. So you might be thinking then, well, how the hell do we draw 3D graphics? Because this is a 3D console, and nothing I've mentioned so far mentions 3D. And the solution to this is we draw 2D in a specific order. Now, if you think about it, if you think about a cube, right? If you have like a rotating cube in space, every individual face of that cube can be drawn with a quad. And so if you just draw those back to front, then what you will see is kind of the front faces of the cube, or whatever the kind of front faces of the cube are for the current rotation, right? And so you'll get what looks like 3D, despite the fact that all the components of it are actually just 2D. And so there's a couple different ways of ordering the sprite specifically. The painted algorithm is kind of the most common one. The painted algorithm it's pretty much just you draw things back to front. That's just kind of how it works. Now there was going to be a code sample here talking about. There was going to be a code sample here, just going through some basic Sega Saturn stuff. Unfortunately, just kind of due to what the homebrew scene is like, and due to kind of the complexity of the system, I kind of wasn't able to get anything that I was kind of particularly happy with. So I kind of just have to skip past that. So the next system is the PS1, and luckily with this, we don't have to go into kind of great detail into kind of understanding it. We can just kind of go straight into it. So the first kind of important chip that the PS1 has is the motion decoder, or typically just referred to as the MDEC. The MDEC is pretty simple. It just plays back FMVs, and this is kind of why, if you think about games from the different consoles of this time, the PS1 was one of the ones that had the most kind of FMVs out of all of them. This is exactly why. It's because it had a chip specifically for this. Other consoles from the time, they could do FMVs, but the fact that they would have to do it all through the CPU, whereas here the CPU kind of is barely involved when you're using the MDEC. So the next chip is the Geometry Transformation Engine, or the GTE. The GTE is pretty straightforward. It's just a coprocessor for vector matrix maths. Unlike the DSP from before, though, it's not user programmable, which makes it so much easier, because you're not kind of at any point having to specify how it should do stuff. You just know, it's going to do this bit of matrix maths for me, and that's it. So it's a lot easier to use. The last chip is the GPU, and you can take a wild guess what that one's doing. So one of the things I think is quite interesting with the PS1 is that VRAM, it's a texture, right? It's not treated as like a big one-dimensional array, which is kind of how memory is typically treated. And the reason for this is because, it's not memory mapped at all. The CPU doesn't have direct access to it. Instead, it has to go via the GPU. And if you think about the GPU, it's only ever dealing with textures, right? It deals with the textures that you give it and frame buffers. But fundamentally, all of these are still textures, right? And so the GPU decides it's going to treat it as one big texture, right? And so it's a big 16-bit per pixel, 1024 by 512 texture, but that's kind of how it treats it. And this is kind of something that you then have to you kind of have to get an understanding for, because any textures that you want are actually just a slice of this big texture. And so when you specify for a 3D model, when you specify with the UV coordinates for it, to draw to draw from a texture, you're having to specify the coordinates in this big texture, because again, they're just slices of it. Now, texture mapping with the PS1, it's pretty weird. So normally, when you do perspective projection, the final step that you do for every pixel is you divide by the z coordinate. Now, this is kind of important, but the PS1 just decides we're not going to do that. And there's kind of a good reason for this. I mean, division is notoriously an expensive calculation to do. But the end result of this is that texture sampling on the PS1, it's always pretty warped, right? And you can see with the example below, you have just a flat plane that kind of samples fine. You have, on the right, you have a plane that's kind of tilted backwards and it's sampling correctly. The middle one is what it would look like on the PS1, where you can see that just the sampling is just not, it's not right. The only real solution that you had, because at vertices it would be correct, and between vertices it would get more and more distorted. The only real solution to this is just to subdivide geometry. But obviously, having to draw more triangles is always going to be computationally expensive. So triangles. Unlike the Saturn, the PS1, it actually has triangles as our lowest primitive. There is an issue with this though, is that just like the Saturn, you're not specifying a Z value. You're only ever specifying an X and Y value for where it should be drawn. And so once again, we do 3D by drawing primitives just in the right order. Now, we're pretty lucky here because the PS1 actually has a very nice solution to this in its library. And this is, these are called ordering tables. Now, an ordering table, it's just a linked list of pointers. And each pointer is just pointing to a primitive. And that's it. And so essentially just to do 3D, you write your primitives to memory. And then you add a bunch of entries to your ordering table based on the Z value that you have. Now that might still sound a bit complex, so I've prepared a code sample here to go through. And so first of all, this is just what the code sample actually looks like. It's pretty straightforward. You have a blue triangle up in the top corner that's static, and we have this pink triangle that's rotating about the y-axis. So if I swap over to VS Code here, we can start to go through this example. So the first thing we've got here is display environment and draw environment. Now, these basically just specify where in that big texture that the GPU has, where we want to be displaying from and where we want to be drawing to. And the reason there's two of these is that we're using this for double buffering, right? And that's exactly what this DP variable here is, it's double buffer. Now, from the examples I've seen, this seems to be kind of the general way that this is represented, so that's kind of why I've done it that way. But yeah. Now the next thing is our ordering table. And again, this is double buffered. But you can see it's just a table of, in this case, ulong, just so we kind of have something that we can write to. That's kind of all that really matters. Now, the ordering table doesn't actually store our primitives, it's just storing pointers to our primitives. And so we then have to store our primitives in some bit of memory here, so that's why we've got to call this primitive buffer. And again, this is double buffered so that we've kind of got 2 bits of memory we can write to for the 2 different back buffers. And the next primitive is just a pointer into this table, so it's pretty simple. So we go straight into main then. We're just going to jump into init graphics instead, because this is what immediately gets called. So the first thing we do is we kind of just reset the GPU, re-enable everything. Now this next part, here and here, these are kind of setting up the display environments for our double buffering and the draw environments. And now one thing you might notice with this is that the numbers here for display environment 0, they don't match the numbers for draw environment 0, but they do match the ones for draw environment 1. And vice versa, with 1 and 0 here, they match. And you might think this is a mistake, but it's not actually. The reason for this is that it means that by default, at first, we're drawing from this region. We're displaying from this region, but we're drawing to this region. And then when it flips, we're now displaying from the region we were just drawing to, and we're drawing to the region that we were just displaying. So we're constantly flipping which area we're drawing to and which area we're reading from. Yeah, okay. So the next part then just kind of sets the drawing environments to kind of clear the background. We set them to have this clear color, which if you pulled this up into an RGB color viewer, this would just be the kind of purple color that you saw before. So next we're kind of just initializing our double buffer variable and our pointer. initGeom just kind of specifies the geometry transformation engine. I need to use you now, so set yourself up. Now, geom offset is quite an interesting part. So by default with this console, the origin isn't actually the middle of the screen. Instead, the origin is the top left hand of the screen. This seems confusing at first, but this actually makes quite a lot of sense. The reason for this is that if you think about kind of treating the entire screen as just one big 2D buffer, as you go along the x value, or as you increase the y, you're going down, and that's exactly kind of why it's treated this way, because that's how it's represented in memory. Now, because of this, all of our perspective transformations are going towards the origin, which means they're going to be going towards the top left corner of the screen, which we don't want. So set geom offset. Pretty simply, all it does is it just all of those transformations, it just offsets them a little bit. So it offsets them by these values, and these coordinates are just the middle of the screen. So we're just kind of making it so that perspective transformation moves towards the middle of the screen. And set geom screen is kind of it's doing a similar thing, but just sets the camera's distance as well. And so lastly, kind of the display and draw environments that we've set up, we just make sure that we're applying the first one, so that we're kind of, we have something to display and we have something to draw from, or draw to. Okay, so this next part is our main loop. Now, clear O tag R, this part, it's a little bit difficult to explain, but essentially there are two different methods we can use for clearing our ordering table. The first one is clear O tag, and the second one is what we've used here, which is clear O tag R. Now, clear O tag R, the R stands for reverse, right? So what this means is that the ordering table is set up such that kind of the first element is the last thing that will be drawn, and the last element is the first thing that will be drawn. And this kind of might seem weird, but actually, if we want to get the painter's algorithm, where we're drawing things back to front, this is exactly set up to do that. And so now, as what you'll see later in the code is that we can just slot things in based on their z value, and things will just get drawn back to front. So okay, so now we can kind of go straight into a draw function here. So draw is kind of just calling these two functions that I've set up. So simple try is that blue triangle that we have in the top corner that was static. So the first thing we do with this triangle is we kind of we get the kind of next bit of free space that we have in memory, and we kind of set poly of 3. Now what this is doing is that the system has to be able to tell what primitive it's working with, because there's quite a few different types of primitives, and so pretty simply it just writes a code into memory to specify, hey, this is this type of primitive. So that's exactly what we're doing here with set poly of 3. Now that we've kind of set the primitive type, we can start to set parameters for it. So we can specify this triangle, we want to use this color, which this is RGB. So B being the only one that's full means that it's going to be blue, which is what we were getting from that blue triangle. So we're kind of then setting just the coordinates, which these are in screen space. And then lastly, we kind of add our primitive to the ordering table, because we've kind of, with this, we've kind of set it up into our primitive buffer, but we need to actually add it to the ordering table for it to be drawn. Now here, kind of where we're adding it doesn't matter too much. I just added it into the first position available, but it doesn't matter particularly where you add it there. And lastly, just kind of so that the next primitive is pointing to the next bit of free memory, we're just going to skip it over size of poly of 3. Okay, so the next one is rotating try, which is a little bit more complex, but it's not as bad as it seems. So let's kind of just go through it first. So positions here, this is kind of just defining the positions for our 3 vertices of our triangle. And current points here is just some working memory we have. Now here we're kind of doing pretty much the same thing we were doing before. Initializing our memory, setting up the type, and setting up the color. Now next, kind of we're initializing some memory. So initializing this matrix that we want to use. And then we're kind of initializing variables for the position, rotation, and scale of our triangle. Now here I've kind of just set the position to be constant. It doesn't matter too much. Rotation here, I've kind of added this rot y value, which is constantly incrementing, so the triangle will be rotating around the y-axis like you kind of saw. And lastly, kind of scale. Now, this is one of the things I didn't mention, is that both the Sega Saturn and the PS1, they don't have a floating point unit built in, so you have to use what's called fixed point. Now, unfortunately, there isn't really a good way to represent fixed point in code. I mean, the fixed point, the version of fixed point integer for the PS1, or the version of 1 is just 4096, but you don't want to have to write that out. So I set up a pretty basic macro here, which you can see exactly what it's doing here. It just kind of takes what's in the brackets, converts it to a double, shifts it so it is in the kind of proper range, and then converts it back to an integer. And all this is done compile time, so that this fundamentally, in the actual code, isn't relying on doubles or floats or anything. Okay, so next we kind of, the matrix that we have, we're kind of setting it to have a rotation based on the kind of vector rotation that we've got here. We're setting it to have a translation based on our position, which we kind of set up here. And then we set it to have a scale, which again we set up here. And now the system kind of has specific bits of memory that it knows what matrices will be used for what. So we're going to specify that we're going to use this matrix for rotation and translation. And lastly, we kind of just, we take the vertices that we've got, we specify these are vertices that we want to transform. This is the memory that we've got that we want to write them to. Do that. And each of these is returning the depth value of that vertex. And the reason that we do this 3 times, there is a function to do this once, but it returns just the middle, the z value of the middle of the triangle. And so instead what we're doing here is we're averaging it, so we kind of get like it's slightly more accurate z value. And so now at this point that we've kind of got, we've transformed these points into this point, we can now just kind of write this out to the screen. Because we've kind of got a z value, we can kind of just make sure our z value is in range, and then we can just slot it into our primitive table like this. And so you can see that kind of the details of how the ordering table work here don't actually matter that much, because fundamentally we only really care that we're kind of slotting it in based on our z value, and that's it. Okay, so the last bit that we go to is display. And this is the only other function that gets called in this example. And so you can see after we've kind of set everything up to draw, we call display, and then we're just updating rot y like I said before. So what display does is it first kind of waits for the system to finish drawing what it's drawing. Now once it's kind of finished drawing, it sets what it's just drawn to be displayed. It sets the new thing to start drawing, and it flips our buffers. So now that we're drawing something here, we'll go through these. We'll go through starting a new set of drawing. We'll wait for this first drawing to finish, and then we'll set a next set of drawing to go, and so on. And so what this means is that we're constantly, whilst the system is drawing to memory, we're setting up the next frame to start being drawn. And yeah, okay. That's kind of pretty much all there is for this example. And so now we can kind of get back into the slides. So the next and last system we talk about is the N64. Now the N64's architecture, it's deceptively simple. It seems kind of quite basic from outside, but it's when you get into the kind of it's when you get into the details that it kind of gets quite complex. Now the first chip we talk about is the RSP, or the Reality Signal Processor. And this is a coprocessor that's used for vector matrix maths. Now, just like the Saturn's DSP, it is programmable, but the RSP is a little bit confusing. We'll kind of get into that later. Now, the RSP, unlike the kind of chips we saw before, it's not just doing maths, though. It actually also handles display lists and sends them over to the RDP. Now, display lists are kind of just, it's a list saying, draw a triangle, draw a quad, draw whatever. It's just a kind of list that specifies how you should display things. And the RDP is the next chip we talk about. So here is the RDP. It's pretty simple. It just kind of handles, actually drawing stuff. So the RSP, it's still doing, all the maths and stuff, and then it sends stuff over, and the RDP draws it. Now, one of the things that's quite fun about the N64 is it uses what's called a unified memory model. So every other system that you've seen here, they kind of had, main RAM for the CPU to use and VRAM for the graphics to use. That's not the case here. Here there is just RAM, and that's it. And so everything is using this one bit of memory. And so something that's an important thing to take away here that will kind of become a bit obvious later is that there is no VRAM. And so I mentioned that the RSP kind of is programmable here, and it's programmable using what's called microcode. So like I said, it's not fixed function. It's able to kind of store a user program. And kind of one of the benefits of this is that during the N64's lifetime, Nintendo actually released quite a few different programs, and they kind of had different optimizations in different ways. Now, unfortunately, they didn't actually give access to documentation for it until very late in the system's life cycle. And so despite the RSP being, it's actually quite a powerful architecture, the system just kind of wasn't able to utilize this properly because developers just weren't given access to it. Now, texture memory is one of the things that's very interesting with the N64, because the N64 is super weird with textures. So the RDP can only draw from textures that are stored in its local memory. And this memory only has enough space for a 64 by 64 texture. And the issue with the RDP is that it doesn't automatically load new parts of a texture into this memory. Loading stuff into the RDP memory has to be done manually. And so if you want to draw a model that has a texture that's larger than 64 by 64, you have to kind of split your texture up first, and then you have to split your geometry up. And so now when you're drawing it, you set the first texture, you draw the part of the model that's using this first texture, you set the second texture, and then draw the part of the model that uses the second texture. And so you can see how it starts to get quite obnoxious, because you have such a small amount of memory there for that texture. So the next part we talk about is filtering. Now both the PS1 and the Sega Saturn use what's called nearest neighbor filtering. And this results in quite a pixely look. Now the N64, however, uses what's called bilinear filtering. Now the N64 filtering is actually quite interesting, because bilinear filtering normally, the way it works is it just samples the surrounding 4 pixels of where you kind of were going to be, and then averages them out, and that's the color it decided to use. The N64, however, instead of sampling from 4 points, it samples from 3 points. And so the result with this is that sometimes textures can look a bit weird. And so to kind of get around this, developers would specifically bake textures to already be warped so that they would look good with this way of filtering. Now, one of the things with the N64 that is my favourite thing is that we actually have a Z buffer. We don't have to do a weird way to draw it. We don't have to do some weird method to draw 3D. We can just draw it. And yes, we actually have a Z buffer. And now I can't say for sure, but I think the reason for this is because out of all 3 of these systems, the N64 is the one to be released latest. And so, the costs of memory had gone down, and so they were able to justify the cost of adding a Z buffer. Now, drawing with the N64, it's pretty similar to the PS1 and Sega Saturn. So pretty much we build up a list of commands, which in this case we call a display list, and then we send that over to the DSP. Now I've got another sample here of the N64. This is actually kind of a sample taken from the official SDK, so I unfortunately will not be releasing the code for this, but you can find it online. And so if we swap over to this, this is kind of the example I was saying about. So there's a lot of things with this. Like I said, the N64 it's a very complex system when you get into the details. We are kind of not gonna. I'm going to skip over quite a bit of this code because we're just talking about graphics here. We don't want to talk about the threading of the system, the OS of the system. We don't really care too much about this. We just care about graphics stuff. So I'm going to skip through quite a bit of this and just get into our main loop. And so the first thing we're doing in this main loop is we're getting a projection matrix, and we're kind of storing it in this bit of memory here, and we're kind of also just getting a rotation, storing it in this bit of memory here. And these are kind of matrices. Next we kind of get glist p here. Now glist p is basically just is a pointer to our display list. And something you might notice here is that every time after we're doing something here, we're doing glist p++. And the reason for this is just so that kind of glist p is now pointing to the next bit of memory that you can write a bit of command to. And so we're going to skip over some of this here because again, they're kind of a little bit outside of the scope here. But here, what we're doing is there are some display lists that are actually defined in this file up here, which I'll show you in a second. And we're going to just use these display lists that you've kind of already got. And then next kind of what it's doing is just based on do texture here as an integer. the system decides whether it should draw a shaded triangle or a textured triangle. But again, it's kind of just drawing it's drawing the display list that we've kind of already got. And so the rest of this code here is kind of, again, it's a little bit out of scope. So we're just going to kind of look at the display lists now. And so I won't go too far into these because, again, complex. But you can see here kind of that these display lists are just initializing the RSP and the RDP. You can see how they're kind of, they're setting up the things that you'd want. So here we're setting up to be smooth shading, we're setting culling on, we're turning on fog. Or we're turning off these things, sorry. And then kind of turning on smooth shading here and turning on shading. And you can see over here that we're specifying we don't want to use any alpha stuff. We want to disable color dithering. So you can see you can start to get an idea of kind of what these are doing. Now this part here of clearing the frame buffer. First thing this is doing is setting this to use cycle fill. This is basically just, there are a couple of different ways that the system can draw to the frame buffer. This is like the quickest way, which when you're just filling the screen with a color, this is kind of what you'd want to do. And so the first thing we're going to do is we set a color. Now, just kind of unfortunately, just due to how these commands are set up, the color has to be packed in twice for some reason. I'm not entirely sure why, but that's kind of exactly what this does here, and you can see the color is the same. And so then we kind of specify that we want to draw a rectangle, which is exactly what we're doing with the bigger rectangle we had at first. So we wait until that's drawn, and then we specify that we want to use a blue color now, and we want to draw a slightly smaller rectangle. And that's kind of, if you think back to the example, that's exactly what we had with the background. We kind of had a bigger triangle that was grey and a smaller triangle that was blue. And so the next thing is shade tri-DL. This is kind of the triangle, or this is the quad that you saw before, sorry. And so here, those matrices that we set up of the rotation and the projection, this is exactly kind of using those bits of memory that we'd specified. We're kind of saying, hey, we want to use this matrix for projection, and I'll load it. We want to use this matrix for model view stuff, and we want to load it again. And so we kind of wait until that's loaded first. We set the system to be in a different cycle node, and we can kind of skim some of the bits here. The kind of important part is we specify this bit of memory here, shade VTX. This is where our vertices are stored, and now we're kind of using indices. And so if you look at this, it's 0, 1, 2, 0, 2, 3, which, if you have any experience with graphics programming, with doing stuff like this from hand, this is actually kind of how the indices tend to be quite a lot of the time. It's 0, 1, 2 for kind of the first three parts of it, and then 0, 2, 3 to kind of set up the last part of it. And now, if we look at these vertices, we can kind of, just from looking at them, we can start to take a guess as to what these values are. So, these three are probably going to be the X, Y, and Z values. These last four are probably going to be the RGB colors of the vertices and things like that. And so you can see how kind of, despite the fact that, there is a bunch of stuff here that I have unfortunately had to skim over just because it is quite complex. There's a lot of things we can still kind of gather from this, just from kind of looking through it. And yeah. So that is kind of the end of the talk. Thank you for listening. If you have any questions, please feel free to kind of reach out to me in the comments below. You can also reach out to me on Twitter. I'll kind of link all my social media and stuff in the bit below. And I'll also be linking a GitHub where you can access that PS1 example from. And so yeah, thank you for listening and thank you for watching.